The iPAVe is the pinnacle of road asset management technology. The Intelligent Pavement Assessment Vehicle, iPAVe, utilizes state-of-the-art traffic speed deflectometer technology integrated with the Hawkeye operating system, enabling comprehensive road surface and subsurface condition assessment in a single pass. It is widely acknowledged that measuring pavement strength has been a difficult, expensive, and unsafe metric to accurately collect. Road networks have historically been managed based on their surface condition, and measuring pavement strength has historically been a difficult, expensive, and unsafe practice. Using traditional methods, 5 or 10 data points in a kilometer can be collected. This is insufficient to enable an accurate analysis of subsurface conditions. The FWD used to gather this data is also slow and relatively dangerous, in that each test takes around 30 to 40 seconds, with the vehicle being stationary and requiring formal traffic control. Conversely, traffic speed deflectometer devices, such as the iPAVe, are capable of continuously measuring pavement response at traffic speed. This means more data points per kilometer can be safely measured. This results in a significantly more intensive insight of structural condition, thus identifying areas of weakness which could go undetected by a FWD or visual condition assessment. The Intelligent Pavement Assessment Vehicle, iPAVe, has been 60 years in the making and is the first fully integrated road surface and subsurface condition assessment system, providing functional and structural data at highway speeds. When using the iPAVe, it is possible to gather a more comprehensive and accurate assessment to more effectively and intelligently manage a pavement section. ARRB Systems introduced the iPAVe to the world in 2013 and has since successfully developed and commissioned several others around the world. The iPAVe is the only survey vehicle to combine the traffic speed deflectometer, TSD, and the Hawkeye, ARRB's functional assessment technology. The Hawkeye platform is responsible for measuring road surface characteristics such as cracking, roughness, rutting, texture, and geometry, together with spatial information and digital imaging. The TSD is made up of 11 high-precision Doppler lasers positioned in front of and behind the axle, which monitor the response of a pavement to the application of a rolling load, providing data that includes continuous pavement deflection profiles, from which bearing capacity indices can be derived and pavement fatigues estimated. The high accuracy and resolution of the iPAVe enables engineers to focus on pavement areas which have structural and surface deficiencies, which could be subject to failure. The iPAVe has proven to be a much more practical method for network-level testing, as well as analysis for pavement design, when compared to traditional pavement deflection measurement devices, such as the falling weight deflectometer. The iPAVe is significantly faster, enabling large networks to be surveyed in a fraction of the time. It also provides a safe working environment by eliminating the need for stationary measurement and traffic control. The key advantages of the iPAVe are as follows. Coverage. An iPAVe samples every meter, a sampling rate that is up to 80 times faster than traditional methods, such as the falling weight deflectometer. Speed. An iPAVe can survey at 90 kilometers per hour, with typical outputs of 500 kilometers per day, dependent on the composition of the road network. Efficiency. With synchronized and simultaneous collection of traditional surface condition parameters, including cracking, the iPAVe can collect all pavement measurements in one pass. Safety. No risk to general public and equipment operators. The toolkit provides full data processing, analysis, and management capabilities on all measured data collected by the Hawkeye 2000 system. The software also allows for full control and synchronization of all raw and processed data streams collected. This is the Digital Laser Profiler, DLP for short, which is the non-contact Class 1 inertial laser profiler, which uses lasers and an accelerometer located in each wheel path to measure the longitudinal profile of the pavement. The roughness data is derived from these measurements. The Hawkeye system measures the macro texture of the pavement surface using 3 non-contact lasers. The 3 lasers are situated in each wheel path and along the center line of the iPAVe. The macro texture is reported as mean profile depth, or MPD. The iPAVe is fitted with multiple digital imaging cameras, which are used to record digital images of the pavement and road assets. The cameras are oriented to ensure that points of interest are recorded in the camera's field of view. All cameras are located and calibrated for scale measurement, which allows for the position of all visual assets to be referenced geospatially. The Doppler lasers are mounted parallel to the vertical plane so that the velocity measurement can be split into the vertical and horizontal components. The horizontal and vertical components allow for the calculation of the deflection slope and consequently the deflection bowl. The Doppler lasers measure the pavement velocity by sensing the frequency shift of backscattered light from a moving surface. The beam of the laser diode is split into 2 partial beams, a reference beam and a measurement beam, which are then superimposed again on the surface to be measured. This results in a 3-dimensional space, measurement volume, which contains bright and dark fringes, which are a certain distance apart. Since the light path length of the reference beam is constant over time, the movement of the pavement generates a dark and bright fringe pattern on the detector, the frequency of which is equivalent to the Doppler shift between the emitted and reflected light. The modulation frequency of this fringe pattern is directly proportional to the velocity of the object. This reflected light is detected by a photodiode, and the electrical signal is digitally processed to determine the frequency and hence the speed. An important aspect when using the iPAVe is an understanding of the approach used to determine the deflection measurements from the measurements of the vertical pavement velocity collected by the Doppler lasers. A numerical integration method based on the area under the deflection slope curve, known as the Muller-Roberts method, has been developed. This proposed methodology by Muller and Roberts fits a curve through a plot of deflection slopes, measured by the iPAVe, versus wheel offset. The deflection profile is then constructed by numerically integrating this plot working from a fixed point at or beyond the edge of the deflection bowl towards the wheel load. This use of a numerical method is an important departure from previous approaches. Constructing the deflection bowl in this manner highlights the contribution of velocity measurements further from the wheel to both the shape of the deflection bowl tail and the accuracy of maximum deflection predictions. A global positioning satellite (GPS) system provides accurate and synchronized spatial location Hawkeye data against GPS coordinates for export into asset management systems. This is the Automatic Crack Detector, ACD for short. This is the laser system the iPAVe uses to automatically detect cracks and gather data on them. 2 Laser Crack Management System (LCMS) laser units are integrated into the iPAVe to create an ACD system. The laser units project a 4-meter wide laser line across the pavement. The laser image is captured by 2 3D cameras, which are mounted off-axis to the laser light source. These cameras interpret the distortions to the straight laser line as variations in the vertical surface profile. Each frame is analyzed to determine the presence of cracking on the pavement surface. The ACD equipment is also used to measure a transverse profile in order to determine rut depth and rut characteristics. The processing software allows both lane and wheel path rutting to be measured using the string line and straight edge models. We also have the ability to analyze the crack maps, various distresses, roughness, rutting, etc. using our own proprietary software. The flexibility of the Hawkeye software allows reporting of the type, severity, and extent of cracking in a manner that meets the specific needs of the user. ARRB Systems has a strong working relationship with the manufacturer of the 3D sensors and continues to provide them with feedback to increase the functionality of the system.